Hey everyone, so today we are talking about Le Chatelier's principle, or Le Chatelier's. I've heard it both ways. Pretty much what this is that we are going to be changing the environment of an equilibrium reaction, and we're going to see how that affects the equilibrium. Will it shift it right? Will it shift it left? We will do things like adding or removing reactants or products. We'll change the temperature. We'll change the pressure. We'll increase the volume. And we're going to see how that shifts our equilibrium. Will it create more reactants? Will it create more products? And it all ties into kind of this letter Q, which is known as the reactant quotient, which kind of tells us which way our reaction is going to shift. So we're going to focus on Le Chatelier's principle first, and then we'll move on to Q. This section is very important. The AP College Board loves to ask you questions about these. Especially, there's some deep thinking ones. There's some really hard critical thinking, problem solving type of questions involving these guys, which you'll see on the test. So make sure you are paying attention and make sure that you are asking questions if you have any on this. The first thing that we're going to focus on with Le Chatelier's principle is, the first thing is the adding or removing of a compound. Alright, if we got a reaction going and we decide to add more reactant or remove more product, it's going to change the equilibrium of our reaction. So let's look at an example of that. Let's say we got just a basic combustion reaction here of methane and oxygen. Alright, and all you need to know is that when I add something to a certain side or remove it, the reaction is going to want to balance itself out. So if I added some CH4, that reaction is going to shift right. It's going to create more products. If I remove, this should be an equilibrium, if I remove CH4, that reaction is going to shift and make more reactants, because if we remove CH4, it's going to say, hey, we need more CH4, we got to shift it left. Same with the product side. If I add more, say, H2O, it's going to shift this reaction left and create more reactants because I'm adding more product. It's saying, hey, we don't need that much product, let's turn some of that into reactants. Same thing if I remove, say, CO2. If I remove CO2, that reaction is going to say, hey, we need more CO2. Let's start making some more and shifting this reaction right. So that's all this is. We're changing the concentration. Maybe we're diluting something. Maybe we're dehydrating something. And it's going to shift our reaction one way or the other. So let's go ahead and let's say that I remove some O2. How is that going to shift my reaction? Is it going to shift it right, or is it going to shift it left? Well, if I take away O2, this reaction is going to say, hey, I need to make some more of that. Let's shift this reaction left. Okay. Let's say that I want to, say, add some CO2. Now I'm adding carbon dioxide. If I add carbon dioxide to this side, right, it's going to shift left. It's going to want to make more reactants. Too much CO2, I don't like that. Let's go left and make more reactants. Let's say I add CH4, right? If I add some CH4, what's going to happen? I add some CH4 here. It's going to shift right. I'm adding more reactants. It's going to want to make some more products. Right. So remember, again, the only things that affect equilibrium are gases and aqueous solutions, or gaseous states. So if this were a liquid, this water were a liquid, and I said add H2O, you would say nothing. Okay? Liquids and solids don't affect equilibrium. So keep that in mind later on. Let's go ahead. So we should be able to understand that adding of a reactant or product or removing of a reactant or product will shift it left or right. Let's go on to our next factor. So our next thing in Le Chatelier's principle that's going to affect the equilibrium shift is increasing or decreasing pressure. So when we increase pressure, we're forcing those molecules to get really close together. So what they're going to want to do is they're going to want to try to limit how many molecules there are. So if I increase the pressure, it's going to shift to the side of the reaction that has less molecules. So if we look at our reaction here, these are just placeholders for actual elements. I have 2 A's and 1 B over here. I have 3 molecules over here. And then over here I just have a C and D, so it's just 2 molecules over here. If I increase the pressure on those molecules, they're going to want to decrease how many people they have in the container. So what they do is they start changing some of this 2AB into C and D to decrease how many molecules there is. So if we're increasing pressure, it's always going to go to the side where there are less molecules. So increase in pressure is going to shift this guy right, because there's less molecules over here. There's only 2 with C and D, while over here there is 3. But what happens if I decrease the pressure? Well, as you guessed it, if I decrease the pressure, this reaction is going to say, hey, I could go ahead and make more molecules because now there's more space. There's not so much force on us. So when you decrease the pressure, it will shift to the side where there are more molecules, like our reactants side. So keep that in mind. If I increase pressure, it's going to shift to the side with less molecules. If I decrease pressure, it's going to go to the place with more molecules. Now let's go ahead and let's say that same amount of molecules on each side. And I go ahead and I say, all right, I'm going to increase the pressure. Where do you think this is going to shift? Nowhere. No shift. Okay? They're the same amount of molecules on each side. They don't care. Them putting in work to shift molecules to one side or the other isn't going to make a difference. So if you increase pressure when the molecules are the same on both sides, it is not going to affect the shift whatsoever. Okay, so that is pressure, and let's move on now to temperature. All right, everyone, so now we're talking about temperature. So if we increase the temperature, how's that going to shift the reaction? And if I decrease the temperature, how am I going to shift the reaction? Well, remember that temperature can be a product or a reactant, right? We could have enthalpy, so we could have heat as something that we need for a reaction to happen, like if it's endothermic, or we could have heat be created as a product. When a reaction happens, heat could be released. So we're going to be looking at that when we're determining which way this is going to shift. So let's say that our reaction is exothermic. Heat is a product. And say that I increase the temperature. I increase the temperature. Well, remember that heat is now a product. So when I increase that temperature, I am essentially adding a product. So if I'm adding a product, which way is this going to shift? Left. It's going to shift left towards the reactant side. Let's go ahead and let's say now that heat is on the left side. It is now an endothermic reaction. And let's say that I, once again, increase the temperature. Remember, now heat is a reactant. Heat is needed for this reaction to happen. So now if I increase the temperature, I'm adding a reactant, and now it's going to shift it right. Okay? And then if I decrease the temperature, it would shift left. But it's not going to be so nice, right? It's not just going to show you heat right here. Usually it's going to show you this in terms of delta H, which let's say at this point is negative 100 kilojoules per mole. So now I'm giving it to you in standard way that you'll see it, and it says negative 100 kilojoules per mole. If it's negative, is it endothermic or is it exothermic? Exothermic, which tells me that heat in this case is a product, okay? So remember when you're seeing that, if it's negative, it's a product. If this were positive, it would be a reactant because it would be endothermic. Well, let's forget about it and leave it negative. And then say I just decrease the temp. Well, if I decrease the temperature, that would take away from my products. That means it would shift right. So that is temperature. So now we know if we add products or reactants what it'll do. Pressure and temperature. And there's only one more thing you gotta know. What happens if I add a catalyst? What if I add something to speed up that reaction? Is it going to cause me to make more products? Is it going to cause me to make more reactants? When you add a catalyst, it doesn't affect the equilibrium. It just affects the speed. This is a kinetics thing. So there will be no shift. It will help you reach equilibrium faster, but it's not going to create more products or more reactants or less of either. Okay, it's just no shift because a catalyst just increases the speed in which a reaction happens. It decreases that activation energy. So let's do a couple examples and then we'll move on to reaction quotient Q. So here is my example. I got phosphorus mixing with chlorine gas here, gaseous state, and it's making phosphorus trichloride. Notice here that phosphorus is a solid. I have a reaction here that is producing or that has some sort of enthalpy of positive 250 kilojoules per mole. So let's go through each of these and determine which way this shifts our reaction. So in A, I am increasing the pressure, right? So I'm making that really close quarters for those molecules. So which way is this going to shift? You guessed it, it's going to shift right. It's going to shift to the place with less molecules. More pressure, they want to clear some space out, get less molecules in there. So they're going to go to the right where there's only 4, where over here we have 6 that affect equilibrium. I add some phosphorus solid. How is that going to affect equilibrium? Phosphorus is a solid, right? Do those guys affect equilibrium? No. So it is no shift. Those molecules are just too close together. They don't really react or really help with shifting the equilibrium in any way. Decrease the temperature. Well, let's look at this. I told you I have an enthalpy here and that's positive. What does positive enthalpy tell me? That tells me that it's endothermic. Heat is on my reactant side. If it was negative, it'd be on the product side, it'd be exothermic. But here it's endo. So if I'm decreasing the temp, I'm essentially taking away that heat, which is a reactant. So it's going to shift left. It's going to shift left. All right, everybody. That is Le Chatelier's principle. Now let's get into that reaction quotient Q and what that means for us. So reaction quotient Q. Before, I was giving you equilibrium concentrations and then you could plug it into your equilibrium expression and you could find K. Or I was giving you some initial concentrations, some equilibrium concentrations, and you'd have to use the ICE table to figure out K or to figure out an end concentration at equilibrium. But here, what I can do with reaction quotient Q is say I give you the concentrations of all the reactants and products right at the beginning or at a certain time in the reaction. Well, if you know what K is, you'll be able to tell me if that reaction will shift right or left. So let's go through this and let's talk about this just a little bit more. So let's say that I just have a reaction. I'm going to come up with one here. Say I have N2 plus 3H2 and it makes NH, what do I have? 3. And they're all gases. And I'm going to tell you what the equilibrium constant is. The equilibrium constant, let's just say it's just 1 times 10 to the 4th. I don't think that's actually it. I just made that up. So what I can do is I could give you a concentration for all these at a certain time. Let's just say they're all at the very beginning what the concentrations are. Let's say that the concentration for this N2, I don't know, let's just say it's 0.25. Let's say the concentration of H2 is 0.6. And let's say the concentration of this guy is 0.5. Okay, so what I'm saying here is these are my initial concentrations, and I'll put a 0 down here to signify initial. And what I want you to do is find Q and tell me which way that shifts. Well, in order to find Q, it's just like equilibrium expression. It's just instead of a K, it's a Q. So let's write our equilibrium expression, C there because it's concentration. Q, right? We do products over reactants, just like we've been doing with our equilibrium expression, K. NH3 squared over our reactants, which are N2 and H2 cubed, because there's a 3 in front of it. And now all I'm doing is I'm plugging in those initial concentrations. Remember, we could only use Q if we have all the concentrations of everything in our equilibrium expression and it's not at equilibrium. It could be at initial, it could be halfway through, but it can't be at equilibrium, or else that would give us our K. So we're going to go ahead and plug in what we know and solve for this. So this will be 0.5 squared, this will be 0.25, and this will be 0.6 squared. And let's see what this goes ahead and gives us. Oh, not squared. You're probably perplexed or still just writing it down, but before you do, it's a 3, not a 2. So I'm going to do 0.5 to the squared divided by 0.25 times 0.6 to the cubed. And that gives me a Q of 4.63. So you have now found Q. Well, what does that tell me? What does Q possibly tell me? Well, it tells you which way or how far or how past your reaction has already gone. Here is something important. If Q is less than K, right? It's still got a ways to go. It's still got to reach equilibrium. So it is going to shift right. So if your Q is less than K, it's still got to keep going. It's still got to create some products. If your Q is equal to K, that means you're already at equilibrium. I pretty much gave you the equilibrium concentrations. So if Q equals K, you are at equilibrium. And then if Q is greater than K, you have gone past equilibrium and things need to come back to balance out and things need to shift left. So in our example here, our Q is a lot lower than our K, right? Our K is essentially 10,000. Well, our Q's got a long way to go. That means that when I put these concentrations in a container together to react, they're going to shift right and create a lot more products because that Q is so much less than the equilibrium constant K. So that is what you're going to be doing. You're going to be plugging some things in and you're going to get a Q, and that's going to tell you pretty much in Le Chatelier's principles way of which way is this reaction going to shift. Is it going to shift right? Is it going to shift left? In this case it shifts right because it's got a long way to go before it gets to that 10,000. Let's do a couple more examples like this to make sure we got this down. Okay, so here's our example. At time 100 seconds. Your pressures are 1.25 atm, 3.5 atm, 7.5 atm of these reactants and products. If Kp equals 1 times 10 to the negative third, which way will your reaction shift? I gave you some pressures here because sometimes we get so caught up in concentrations that we forget that equilibrium is also affected by pressure as well. So what we're doing is they gave us a Kp and they gave us these pressures at a certain time. So we want to figure out which way it's going to shift, so we need to figure out a Q, right? They didn't give us any change in the atmosphere, they just want us to figure out which way it's going to shift. So if we want to find out our QP now, we got to make a equilibrium expression for Q. Products over reactants, NOCl squared, because there's a 2 in front. NO squared, because there's a 2 in front. And then just Cl squared, or Cl2, sorry, not Cl squared. Let's plug in what they have given us now. NOCl's is 7.5. And we'll have to square that. NO's is 1.25. And we'll have to square that. And Cl's is just 3.5. Let's go ahead and plug that into our calculator and see what happens. 7.5 to the squared divided by 1.25 to the squared times 3.5 to the squared, I don't think is a thing. All right, so then we get a Q of 10 point, let's see what I get, 29. So that is our Q. So now which way is our reaction going to shift? Well, remember, Kp is 1 times 10 to the negative third, 0.001. So this reaction is telling me right now I have way too many products, right? Usually this thing at equilibrium is a small number like 0.001, but right now it's at 10.29. So this thing is going to shift left. It's going to create a lot more reactants. That pressure is way too high right now at that NOCl. Maybe something happened, maybe somebody added pressure to it, or just put way too much NOCl in there. It's going to shift left and make a lot more reactants. So we're going to say left. All right? Now let me show you, I just got 2 more examples. Let me show you an example of what you'll see on the AP exam, what they love to show you. So here is a common AP question we see all the time. Let me change this real quick. I forgot I changed it. But anyway, it says, here's a reaction. I got Na and OH, and they're in equilibrium with sodium hydroxide. It says at equilibrium, I have 100 milliliters of a container with a concentration of each of these species. So Na plus OH minus or NaO. If I dilute the solution to 1 liter, will the concentration of NaOH increase, decrease, or stay the same? They love giving you problems like this because they want to try to trick you. They think, oh, I'm adding more water, right? So that means that if I add more water, this is going to probably dissolve this more and give me more Na plus and OH minus. That's what you'll think. That's what I thought when I saw questions like these. But you have to use some sort of calculation to justify your answer. And the best way for us to do that is by using that reaction quotient Q that we just looked at earlier, okay? So what we're going to do, they didn't give us any concentrations, which is weird. All they told us is that we're pretty much diluting it by a factor of 10. So pretty much what we can do here is we could give our concentrations any value and just know that since each one is getting cut by a factor of 10, we could pretty much predict how our equilibrium is going to shift. So let me show you how we'll do that. So originally, right, we will have a Q expression of products over reactants. Essentially, NaOH over Na plus and OH minus. Okay, so essentially, I have this reaction here. That was at equilibrium, but then I diluted it by a factor of 10. I added 900 milliliters of water, so now everything is a factor of 10. So pretty much what I could change this Q to is I could change it to 1/10 NaOH. I could change it to, now I'll have 1/10 of Na plus, or I could change it to 1/10 of, say, OH minus. So what does this mean? Well, let's just simplify as much as we can, right? We know essentially this is going to give us some sort of expression, but let's go ahead and solve these real quick. So 1 over 10 times 1 over 10 is 1 over 100. 1 over 10 divided by 1 over 100 is going to be 10. So let's look at this. Right? So go ahead in your calculator if you want. Take 1 divided by 10, which is 0.1, divided by 1 divided by 10 times 1 divided by 10. That's essentially what's down there. And we hit equal and you get 10. Okay, so pretty much our Q has just increased by a factor of 10. So remember, this was originally at equilibrium. So originally at equilibrium, K equaled Q. Right? It was at equilibrium, so K was going to equal Q. But then we diluted everything by a factor of 10. So now, since all the concentrations have been reduced, our Q has now essentially become 10. Well, if 10 is greater than 1, that means you have too many products, right? So we have too many products. So which way is this going to shift? It's going to shift left. Okay, so what we're essentially doing is we're just putting in the factor of which everything changed. We're going to take these numbers here to get a whole number there. We're just ignoring these concentrations pretty much overall. And then we're assuming that our equilibrium is at 1, right? So we're assuming that since we got a factor of 10 here, that's greater than 1, it's going to shift everything left. So when it's asking us, will the concentration of NaOH increase, decrease, or stay the same? It is going to decrease. Okay, since that Q was 10, everything's going to want to shift back left to this side. We added a bunch of water, spread everything out. So now this is going to decrease. The concentration of NaOH is going to decrease and cause a shift left. Right? Let's do another example like this to make sure that we have this down. So yes, the addition of water did create an increase in Na plus and OH minus. But let's do an example where that might not be the case. So last example, I got calcium hypochlorite, I got water, and they make calcium hydroxide and hypochlorous acid. So at equilibrium, I have 100 milliliters of these compounds at a certain concentration. If I dilute it to 200 milliliters, will that increase, decrease, or unchange the concentration of HOCl? So again, I'm changing now the concentration of pretty much all of these guys. And I want to see how that is going to affect my concentration or my equilibrium. Is it going to shift it right? Is it going to shift it left? And then we'll be able to tell if that increases HOCl or decreases HOCl. So let's go ahead and do that. Let's write a standard Q reaction for this. Products over reactants. So we got CaOH. We have hypochlorous acid, which is going to be squared. Now we have CaOCl. And then do I include water? No, it's a liquid. Forget it. We don't need it. All right? So that was the original equilibrium concentration at the beginning. Since it's at equilibrium, this is essentially K. But now we are diluting it by twice as much, right? We're adding 200 milliliters, so that means we're cutting the concentration of all these in half. So let's go ahead and let's demonstrate this as if it was half. We would have half of our calcium hydroxide. We would have half of our hypochlorous acid, and we would have half of our calcium hypochlorite. So again, this is not a 12, this is a 2. So again, we're just going to combine all these fractions and see how that affects our K overall, or our Q overall, I should say. So this will be 1/2, this is 1/2, but remember it is squared, so then that'll be 1/2 times 1/2 again, which is 1/4. So we'll have 1/2 times 1/2 times 1/2 again, divided by 1/2. Let's see what that gives us. So I'll have 0.5 times 0.5 times 0.5, that gives us the top, and I will divide by 0.5. And that leaves us with just 0.25. So we now have pretty much 0.25 of our original K. So now we have less than what we should have had at equilibrium. So if we have less than our original K, it's now a quarter of that, it is going to shift right. So if it shifts right, it's less than K. It's now a fraction of what our original K is. It's going to shift right. If it's shifting right, it's going to produce more CaOH and HOCl. So in this case, it's asking, will that increase, decrease, or unchange the concentration of HOCl? It is going to increase the concentration of HOCl. Please let me know if you have questions on this. This stuff is kind of confusing. It's brand new. Q is kind of an interesting thing. We will do a POGL on Q to help do a deep dive on this, but please ask questions if you have them. I'm sorry this lesson was long. That's why we're not having a quiz today, okay? But anyways, please let me know if you have any questions. Have a great day.